stunning fireball lights up the night sky over Canada, carrying secrets from the far reaches of space.
When we saw the fireball event on September 25th, I was very excited about it because I knew that there was a distinct possibility of having recovered fragments from it.
Cutting-edge technology makes this meteorite's fall one of the best documented in history.
So we're able to use all of these different techniques to give us a complete 360 view of a meteorite.
Now the race is on to recover fragments, and some turn up in the most unlikely of places.
I heard a loud crash.
Earth's latest visitor could provide answers about the origins of life and the beginning of our solar system.
One of the basic science questions, how did life begin? The answer to that may absolutely be tied up in studies of meteorites.
September 25th, 2009. The astrophysics lab at the University of Western Ontario is empty. A lone camera sits perched on the roof, watching the sky. It's one of 7 cameras in the university's all-sky camera network. They are constantly recording to find what they're looking for: fireballs from outer space. At the same time, 100 miles up, a meteor hurtles toward Earth at a blistering 46,000 miles per hour.
As it approaches the Earth, it starts to accelerate as it starts to feel the Earth's gravitational pull. And at that point, everything changes.
Now in gravity's grip, the space rock picks up speed. If the meteor survives the impact, the camera data will allow scientists to mount a search to try and find it. But surviving this journey is easier said than done.
So as the rock comes into the Earth's atmosphere, it's moving something like tens of times the speed of sound. So it's moving 10 or 20 times the speed of a rifle bullet, very, very fast.
Now, 60 miles from Earth and just 3 minutes to impact, the meteor slams into the atmosphere like a ton of bricks. The white-hot rock burns at over 2,000 degrees.
At that speed, the air molecules start to heat the surface. And as the surface gets hotter and hotter, material begins to come off of it. And that's actually what produces the light that we see in the sky as a meteor.
The meteor is now a fireball, and it tears through the atmosphere on a collision course with Earth. Just after 9 p.m., the sky over Ontario lights up. All 7 cameras of the Canadian network capture the burning fireball, tracking its trajectory through the atmosphere. The freshly fallen meteorite could provide important new evidence about the origins of the solar system, and even how life began here on Earth.
Meteorites represent the earliest history of the solar system. We do not have samples elsewhere from any other source that represent that very early first few million years of solar system history. The only record we have of that we can study in laboratories here is from meteorites.
Most meteorites are small pieces of asteroids, the material left over when our solar system formed roughly 4.5 billion years ago.
The ages of meteorites allow us to determine some very fundamental properties about our solar system. They have been samples that have shown us the formation ages of our own solar system. 4.56 billion years ago, the solid matter came together to form these solid bodies. These are messengers to us. They're delivering a wonderful message of what has happened through the history of our cosmos.
So it really gets at origins. It's all about the origin of the Earth, the origin of life, to give us a deeper understanding of where we come from, both in a biological sense and in a physical sort of earth science sense.
Meteorites fall to Earth every day, but with 2/3 of the planet covered by ocean and most of the land uninhabited, they are rarely found.
In order to have any sort of reasonable prospect of recovering a meteorite from a bright fireball, you need to monitor a huge area of the Earth or monitor a small area in the atmosphere for a long period of time. So typically, camera networks are set up, they have to be able to run for years or decades to have any sort of chance of recovering one meteorite from one fireball.
Planetary scientist Peter Brown operates the University of Western Ontario's all-sky camera network.
This is one of the 7 cameras in the network. So on the night of September 25th, the cameras were running. It was about an hour or so after dark, and there was a very bright fireball that from this particular camera was seen to come in roughly like this. We're actually covering somewhere in the neighborhood of about 100,000 square kilometers with the network. Each camera is seeing out to, say, 300 or 400 kilometers from the actual camera position. So we're covering a lot of southern Ontario, part of the Michigan, Ohio, and certainly all of the Great Lakes.
But this network also uses sound and radar technologies to watch the skies.
So that's something that is very unique in the world. There's no other network that combines all those technologies to look at meteors, a single meteor, using all of those different techniques.
Radar detects the invisible trail of electrons that the fireball leaves behind. And infrasound sensors detect the shock wave that it makes as it tears through the atmosphere.
Our real science goal is to try to observe events in great detail with each of these technologies, and then by looking at the event from all of these different angles, piece together a complete reconstruction of its initial mass, in its initial orbit, how it broke up in the atmosphere.
There are 4 infrasound stations that picked up the September 25th fireball.
By having 4 elements in the infrasound array, we can figure out where the source is coming from, and also we can figure out what is the apparent sound velocity that approaches the infrasound array.
Elizabeth Silber and Zbigniew Szemenski are part of Peter Brown's team and help maintain the infrasound installations.
This sensor has the purpose to register very tiny pressure waves in air. These are usually below the human hearing range.
This infrasound device can pick up low-frequency sound from everything from shuttle launches thousands of miles away to lightning storms and even Niagara Falls.
So we're able to use all of these different techniques to give us a complete 360 view of a meteor. It gives us a huge amount of information, an awful lot of data about each event that enters the atmosphere.
In all, the fireball detection network consists of 7 all-sky cameras, 4 infrasound arrays, and 6 radar stations. They're watching the skies around the clock, searching for Earth's next visitor. On the night of September 25th, these devices record the fireball event, collecting an unprecedented amount of data.
We're actually really fortunate. We've only been running this network for 4 to 5 years, and we sort of won the cosmic lottery in some sense because of that one event.
Initially, what we needed to do was to work out what the trajectory was through the sky and work out what the possible fall locations on the ground were.
Peter Brown and his colleague Phil McCausland begin to pore over the data from the Ontario fireball. Their goal, to calculate where it came from, where it may have landed, and mount a search to find it. The meteor first became visible to the all-sky camera network when it turned into a fireball through a process called ablation.
When a rock arrives at the Earth's upper atmosphere, starts entering and starts really slowing down, the main process that goes on initially is the material gets stripped away from it.
The rock literally vaporizes from the intense heat.
We see it as a trail of sparks flying behind the main fireball. It's just little bits and pieces getting stripped off and becoming independent little fireballs.
The cameras captured the entire process.
We're seeing feed from each of the cameras from the network. So each of the cameras is pointed straight up. What you're seeing here is an image showing the entire sky. So right in the middle is directly overhead as seen from the camera site. And around the sides here, you're seeing the horizon. The fireball actually passed almost directly over the camera. Very fortuitous, just the geometry was just right.
Capturing the fireball's descent from multiple angles enables Brown to pinpoint its exact location.
One of the key things is that the fireball penetrated very deep. So getting down to 20 kilometers altitude is extremely unusual. In fact, it's basically the deepest of any object we've ever detected in 5 years.
The deeper the fireball penetrates the Earth's atmosphere, the more likely it is that scientists can recover it.
As the rock gets deeper in the atmosphere, it basically hits a brick wall. It hits the thicker part of the atmosphere and shatters. So whatever's left of the rock gets crushed.
During the mid part of the flight where you see all the bright flashes, there are lots of pieces being released. It's fragmenting, there's lots of light. Some of those pieces are gonna fall down, but right at the end here, you can see there's sort of 5 major fragments that are left.
The smaller fireballs begin to slow down to speeds of 6,000 to 9,000 miles per hour. They also start to cool, and when they finally extinguish, they become invisible to the cameras.
That process is called dark flight because there's no luminous phenomena associated with that stage in the meteorite's flight. And of course, that ultimately ends in rocks on the ground.
The scientists will try to recover one of these meteorites. And the combination of this video, these infrasound readings, and this radar data could help them trace its journey back to its origins in space.
What's really cool about that is you can take the rock that you have in your hand and you can go backwards. You can take it through the fall event back into the orbit that it had before it hit the Earth and make some reasonable estimate about where it came from in the asteroid belt.
Fireballs from space, like the one over Ontario, put on an otherworldly display when they enter our atmosphere. In 2008, a police cruiser's dashboard camera captures this fireball descending over Canada. And in 2010, amateur video captures this fireball over Wisconsin. But one of the most widely seen meteorite falls in recent history was this fireball over Peekskill, New York. It fell on October 9th, 1992, and was seen by thousands in the eastern U.S.
Peekskill fireball was an excellent example of a really bright fireball occurring over a populated area on a Friday night when there were lots of football games going on, and so there were about over a dozen videographers who happened to catch images of this fireball as it was passing over the East Coast.
Moments after lighting up the sky, a 28-pound space rock slammed into the back of this Chevy Malibu.
That just came out of nowhere.
16 different people capture the fireball on their camcorders.
But I got it on tape.
But when it comes to recovering meteorites, amateur video can't replace the precision of a fireball camera network.
Casual video data is certainly valuable, but you're going to get a lot more information from a sort of dedicated camera network that's set up with the intent of seeing these bright fireballs that are produced.
Brown captured the 2009 Ontario fireball on 7 strategically placed cameras. It's looking to be the best documented meteorite fall to date. If he can recover the freshly fallen space rock, it could provide a wealth of new information about the origins of our world. But the camera data is only the first piece of the puzzle in detecting the meteorite's location. When the fireball arrives, the 4 infrasound elements detect the sound it makes when it impacts the atmosphere.
Meteors, when they enter the atmosphere, are moving much faster than the speed of sound, so they generate a shock wave when they enter the atmosphere. This is the actual sound arriving from the fireball.
Fireballs can make some audible sound when they arrive on Earth, but infrasound is below the range of human hearing. These sensors are designed to detect it. A large shock wave means a high-energy fireball.
The camera tells us that the fireball is moving 21 kilometers a second, and the infrasound tells us that the mass must have been about 50 to 100 kilograms.
That's the equivalent of a 220-pound chunk of cement hurtling to Earth at more than 45,000 miles per hour. Brown uses radar data to confirm the fireball's speed and angle of entry.
A radar, like an airport radar, it operates on the same principle, but the wavelength is much smaller.
The radar detects an invisible trail of electrons that the fireball leaves in its wake.
We actually get a very precise measurement of speed and its direction.
These colored bands are the radar pulses bouncing off the electrons as the fireball gets closer to impact.
We're seeing a whole bunch of sort of complicated interference patterns here. This indicates the object is starting to break up.
At that point, we were really trying to get a good initial solution so that we could figure out what the path was through the sky and make a really good prediction about where the end point was and where pieces might have come down. That was our effort number one at that point.
As one of the best documented fireballs to date, the data will do more than help these scientists recover a meteorite. It will also allow them to trace its journey back to where it came from. Most meteorites come from the asteroid belt, more than 250 million miles from Earth, between the orbits of Mars and Jupiter. It is a dense cluster of giant space rocks, ranging from the size of a truck to the entire state of Texas. When asteroids collide, they eject small rocks, setting some of them on a collision course with Earth.
So the way we study asteroids and try to understand what they're made of is we look at the light that's reflected from the asteroids. We use telescopes on the Earth to look at that light, and that light tells us what the asteroids are made of.
This is called spectral data, and it can reveal the basic properties of the asteroid's surface, like color, reflectivity, and composition. And radar can also provide these murky video images of the asteroids tumbling through space.
Another way we study asteroids would be to collect material from the asteroids. That's sort of the holy grail of studying asteroids. We do that every time we collect a meteorite.
Tracking these meteorites, tracking them to specific comets, specific asteroids, or even planets is vital to understanding the origin of life and how life began and formed.
Ice-covered asteroids in ancient collisions with the Earth may have delivered the water that formed our oceans. Other asteroids may have also delivered the seeds of life itself.
Many of the meteorites that land have some amount of organic material associated with them. This material would be amongst the material that was supplied to the early Earth when the Earth was forming.
The best way to test these theories is by studying the materials in meteorites. Because the only other time scientists were able to go out and retrieve a sizable rock from space was during the American and Soviet missions in the 60s and 70s.
Beautiful, just beautiful.
Today, the closest we've come is Japan's unmanned asteroid explorer called Hayabusa. It launched in 2003 for its mission to return an asteroid sample. In June of 2010, it returned to Earth in a brilliant fireball over Australia. But it was unable to bring back any significant-sized samples from the asteroid. Back in Ontario, the data is indicating pieces of this meteorite most likely survived the trip through the Earth's atmosphere.
When we saw the fireball event on September 25th, I was very excited about it because I knew that there was a distinct possibility of having recovered fragments from it. So then the race is on to try to figure out where the fragments came down.
But the initial estimates don't look promising.
When we looked at the initial camera data, without really doing any measurements, just very crude look angles, we thought, oh, this might be just over Lake Ontario, so probably it went into the drink. As soon as we did a little bit more quantitative analysis in the early part of the next week, we realized that, in fact, the endpoint was just over land.
Now, for the final piece of the puzzle, they need to get their hands on the meteorite before the Earth's environment starts to degrade it. But first, they have to narrow the search area and calculate the meteorite's strewn field.
I mean, the Bruce Trail more or less is through here, so maybe that trail...
Strewn field is basically a measurement on the ground of where pieces have landed. An initial meteoroid that breaks up into a bunch of pieces, small stuff, big stuff, it lands in a pattern on the ground, and that pattern forms a strewn field.
Strewn fields are drawn in an elliptical shape, somewhere below the point that the fireball explodes. The larger, heavier pieces of the Ontario fireball continue along their path and fall to the ground first, while the smaller, lighter pieces don't travel as far.
What we're doing when we're searching is we're looking for some happy medium in the searching, because the biggest ones of all, there's only going to be one or maybe a few of those at most. Whereas something smaller, about mid-range, there'll be a lot more of those, and so it's more likely that we'll find them.
I think in terms of what we have from the cameras, at this scale, if we go all the way back out, the fireball would have been coming from roughly this direction. And then the fireball continued on, and the last piece was visible at about 20 kilometers altitude. There could be, gram-sized pieces out in this area.
The scientists think they've pinpointed the strewn field, and the search needs to get underway before weather takes its toll on the newly arrived meteorites. Scientists from the University of Western Ontario believe they've identified the best place to look for meteorites from the Ontario fireball: the nearby town of Grimsby on the shores of Lake Ontario. As Phil McCausland mounts a search in Grimsby's surrounding farmland, the potential for what he might find is limitless.
The really exciting thing for me about meteorite falls is that they come out of the blue, literally, and you never know what's going to be delivered. There is always the opportunity for surprise.
It could be something incredibly bland and normal, or it could be something incredibly amazing, like the Allen Hills meteorite.
The Allen Hills meteorite is among the most groundbreaking and controversial space rocks ever found. A team of scientists discovered it on the ice sheets of Antarctica in 1984 and sent it to NASA. There, scientists determined it wasn't a piece of an asteroid, but of the planet Mars. But what is most surprising about the meteorite is that NASA says it could be carrying the first evidence of life elsewhere in the universe.
We found what we term fossils, possible fossils, in that meteorite.
At NASA's Johnson Space Center in Houston, Texas, David McKay is leading a team of NASA astrobiologists in the investigation of the Mars meteorite. They use sophisticated dating techniques to reconstruct its journey to Earth.
The Allen Hills meteorite was knocked off of Mars 16 million years ago. It traveled through space until 13,000 years ago, when it encountered the Earth's gravitational pull, and it fell through the Earth's atmosphere and landed on the ice fields of Antarctica.
NASA currently has 2 rovers operating on Mars, but no way of getting physical samples like Allen Hills.
This was amazing to the scientific community. We had a sample of the surface of Mars.
From the outside, it looks very ordinary, the size of a grapefruit with a dull green color. But hidden inside are these microscopic golden discs called carbonates.
This is about the size of a human hair in diameter. If you cut a hair across, it would look like this in cross-section, about that size. Now, as we look at this gold circle here, it looks a little bit like a gemstone, and to us, it's like a gemstone. It's really valuable, and it contains the secret of the formation of life on Mars, really.
In geology, the presence of this kind of carbonate material usually means it came from a place with water. The Mars rover missions have confirmed that Mars once had and may still have water. And where there's water, there could be life. The team believes that fossil evidence of life on Mars may be hidden inside these carbonates. But to see the fossils, they need to slice off an impossibly thin sample. To do that, they use this state-of-the-art device called a focused ion beam, or FIB. They start with this small piece of meteorite. The FIB is so precise that it is able to etch words onto a sample smaller than this human hair.
One of the really neat things about studying samples, whether it's samples that you go to a planet to bring back or samples that fall from the sky like meteorites, is that you can study those samples with new tools as new tools become developed. If you send out a robot to explore Mars, you're pretty well stuck with the instruments that were around at the time you made the robot. But if you bring back samples of Mars, you can study them with new technology every year.
This is the surface of the gold carbonate, seen at 1,200 times magnification.
We can remove a piece of the Allen Hills carbonate and thin it down to electron transparency about 100 nanometers thick.
That's 1,000 times thinner than a sheet of paper. The FIB lifts the tiny slice of carbonate out of the meteorite. It is too small to be manipulated by hand, so it is micro-welded onto this much larger sample holder, still barely visible to the naked eye. Team member Kathy Thomas-Kepperda prepares the sample for the next phase, examination under a powerful electron microscope.
So what we're seeing in this view is a magnified region of the golden part of the carbonate disk. As we increase in magnification, we see the darkest little tiny regions are the magnetites that we're interested in studying.
The magnetites are magnetic black minerals. The NASA team believes that they contain fossils produced by primitive bacteria that once lived on Mars, similar to primitive bacteria that presently live on Earth.
This is a single magnetotactic bacteria, not from Mars, but from Earth. And this picture shows that these little guys have made chains of magnetite within their bodies. Now, if this bacterium dies, what happens is that the cell body rots away, but the magnetites are very stable. They don't rot away.
McKay and his team believe that the magnetites in the Allen Hills meteorite may have formed the same way, created by bacteria on an ancient watery Mars. The discovery is still being debated in the scientific community, but if true, its impact could be enormous.
We still are trying to convince the bulk of the scientific community that we're correct, and there's still a lot of resistance to it. I think that there's still a basic question that is important to science, and it's important to philosophy, religion. Are we alone, or is there other life in the universe?
Part of the answer could come from the Grimsby fireball, the latest meteorite to fall to Earth, if the Ontario team can recover it.
We could have something like another Allen Hills land with a witnessed fireball event. You know, and you never know, something like that could happen.
The search for meteorites is underway in Grimsby, Ontario.
It was now just a matter of actually finding pieces. And at that point, the best thing for us to do is to take it to the public Everybody who lives in the area can search for fragments from this meteorite.
Phil McCausland organizes groups of local volunteers to begin searching the town's rural areas. This farmland is in the heart of the fireball's strewn field, or area most likely to produce meteorites.
This is a kind of a hot spot to search within this broad ellipse here. So I've kind of put a big ellipse on here that generally represents where we think pieces came down. We're hoping that this field has enough area that we might have 1 or 2 or maybe 3 of these 100+ gram fragments.
This local rock is roughly the size of the meteorites that the group is searching for. Their strategy is simple. Systematically walk straight lines through these fields.
We're looking for the unusual. We're looking for things that are basically out of the ordinary. So we keep on walking our way, slowly progressing westwards, and probably, in about an hour's time, we'll come to the end of the paddock over there, and we'll have covered this whole hillside.
Fallen meteorites can lodge themselves in the ground, so the team will search just below the surface.
We're going to be walking with these sticks. It has a little magnet on the end. The magnet is attracted to the metal in the meteorite, so it'll be a little bit sticky to the meteorite. Yeah, anytime you feel like you want to check something out, just slow down, check it out. Don't feel the need to have to keep up with the team or something like that.
Almost immediately, something catches their eye.
Oh, that's really cool.
The way it's lying, the size and shape.
Yeah.
But McCausland immediately sees signs that it's not a meteorite.
Now, the only thing is, I pulled this away and it's got moss grown around it, so no, it's not freshly arrived on Earth. It's, it's been there several years.
After more searching, McCausland sights a strange depression in the mud.
Right about there, something sticks. Something down there. The main reason why this is interesting is because in all of the field that we've walked here so far, all of this field basically looks something like this. It has the remains of the soybean around, it has scattered rocks around here and there. This is a clear patch. Anytime you see the unusual, it's worth checking out. There's no particular attraction to anything down there. I haven't found a solid object down there yet either. Oh, there's one. There's a solid object.
But it's a false alarm.
That's a rock, but not a meteorite.
Rocks here on Earth don't provide scientists with much about our planet's history or the formation of the solar system.
The meteorites are a unique record that we don't, for instance, have anywhere on the surface of the Earth. Everything that we have on Earth has been reprocessed by the Earth's weathering, by its geological processes. So nothing on Earth is as old as the beginning of the solar system.
Meteorites provide another piece of the puzzle. Samples that would otherwise be beyond scientists' reach.
Meteorites are wonderful examples of a poor man's space probes. That is, meteorites allow us to have samples of our heavens, samples from the asteroids, samples from the moon, and samples from Mars. These samples are delivered to us on the Earth without a cost of having to prepare a mission.
There are many types of meteorites, each of which can tell a different story. One of the best collections can be seen at the Royal Ontario Museum in Toronto.
Meteorites, they all hold a key, they all hold a piece of the puzzle to the picture of how our solar system was formed.
Even the most common meteorites, a stony variety called chondrites, can yield a lot of important information.
They're called chondrites because they have these little ovoid bodies in them called chondrules. It's a Greek word meaning grain. But this is definitely the most common type. They represent 80–90% of the known types of meteorites.
These chondrules are some of the oldest solid objects in our solar system. They're like snapshots of the dust and gas cloud that was our early solar system before it formed.
These are precious things from outer space that tell us of the distant past. I mean, I'm holding something that's 4.5 billion years old. That's not something you can do every day.
Meteorites are more than time capsules from outer space. They also can provide a vital glimpse of what's happening deep inside our own planet.
This is a very rare meteorite called pallasites. This probably represents what the deep, really inaccessible regions of our planet is like. This is like a core mantle boundary, so we're thousands of miles into the interior of our planet where we just can't go. But the same processes that formed our planet also formed these asteroidal bodies.
And these iron meteorites represent the Earth's molten metal core.
They're quite heavy because they're composed almost entirely of iron and nickel. It's a space anvil, as we sometimes call them. We think these things represent the core of an asteroidal body. We think they're analogous to the core of our Earth, similar composition.
The dark layer on the outside of the meteorite is called a fusion crust. It's the result of intense levels of speed and heat that the meteor experiences during the violent fireball phase of its entry.
Meteorites hit the atmosphere at hypersonic speeds, like going from Toronto to New York in 30 seconds. So these things get super hot very quickly. They become white hot and begin to melt. So the molten material is being ripped, literally ripped off the surface, and is being gouged out as though it was just like putty.
Among the rarest classification of meteorites from the asteroid belt are carbonaceous chondrites.
As you might think, they have carbon in them. There are certain meteorites like the Murchison carbonaceous chondrite, which is famous for containing over 92 different types of amino acids. We know amino acids as the building blocks of life.
It is this type that has sparked the theory that meteorites may have delivered seeds of life to the Earth, and possibly to other planets in the universe.
One of the basic science questions that nobody can answer right now, how did life begin? The answer to that may absolutely be tied up in studies of meteorites.
The Grimsby meteorite could provide these answers if this team can find it. On the night of September 25th, 2009, Tony Garczynski is watching television at home in Grimsby, Ontario. His mother's SUV is parked outside. Just after 9 p.m., something smashes into the windshield.
I heard a loud crash. It basically sounded like a hockey ball off of a garage door. The hollow sound of a garage door getting hit. I didn't think much of it at the time.
The next morning, Garczynski goes outside and discovers the damage.
It came in about this angle here. This is where it shattered everywhere, indented in the laminate. And then we found the pieces on the ground around this area here.
He also notices something strange about the rock itself.
What was weird about it was all black on the outside. Not from anywhere around here, that's for sure. So just kind of wanted to find out where it came from.
Once the fireball and the meteorite search makes the news, Tony and his mother Yvonne realize they've found something special.
I got in contact with Phil McCausland. I saw his advertisement in the paper, and we went from there.
As soon as I just saw it, I said, "Congratulations, you've got a meteorite." It was that obvious.
Brown shares their findings with the local press.
3 weeks ago today, there was a very bright fireball seen all over Ontario. Last week we talked about that in the press. If you were standing right here at the time of that fireball, just over in this direction, you would have seen a very bright light. There would have been lots of explosions. The whole neighborhood would have lit up.
The meteorite is roughly the same size as a golf ball.
It was really great to have that first piece found because that's the big hurdle. Because right then, once the Garczynski's piece was found, and it was obviously a freshly fallen meteorite.
One telltale sign is something called a fusion crust. It's the burnt black exterior created during the fireball phase.
It's unearth-like to see this in a rock. You have a rock with a very thin outer coating that has melted, and yet the whole interior of the rock is unaffected by this melting event as it came in through the atmosphere.
McCausland can immediately decipher some details of this meteorite's fall to Earth.
Out of any given fall event, some small fraction of meteorite fragments will actually have been oriented as they came in. So they didn't tumble like most fragments when they came in through the atmosphere and developed their fusion crust. They actually will have oriented instead and had a front face. It's almost like a re-entering spacecraft. They'll have a front nose that takes most of the heat, and then the rear section here ends up having this sort of much lighter fusion crust, very, very thin.
The Grimsby meteorite is relatively small, but the infrasound data, which helps determine mass, shows that it probably came from a meteor that weighed several hundred pounds when it first hit the upper atmosphere. The scientists are convinced that there are more, much larger pieces still out there. Local volunteers and meteorite hunters continue searching for more pieces. But Brown and McCausland immediately begin studying the first recovered fragment. They may be able to trace the meteorite back to where it came from, somewhere in the asteroid belt, or even a distant planet. But first, they want to see what's inside this latest visitor from space.
Once we recover a meteorite, what we're interested in trying to understand is what kind of meteorite it is. So we'll study minerals that are present, the kind of elements that are present.
Basically, we're bombarding this location with X-rays, and the location of the peaks gives us a fingerprint, a characteristic fingerprint for each mineral.
This machine, called a micro-XRD, allows McCausland and geologist Roberta Fleming to determine what type of meteorite this is.
We've got a pattern, and the pattern has some peaks representing these major lines there.
These patterns produced by the X-ray reveal specific levels of iron and a mineral called olivine. This analysis allows them to classify the Grimsby meteorite as an H chondrite, one of the most common types. But for these scientists, that is a good thing. The wealth of information collected on the Grimsby fireball makes it a potential standard bearer for understanding meteorites.
So this is the first time that we have the complete event all taken from different angles by different types of instrumentation. So we can really start to reconstruct what happens during a typical meteor event that delivers meteorites to the Earth. So this stands a chance anyway of becoming sort of the prototype event that we will refer to in the future as this is what we think standardly happens with this class of meteorite.
More than 80% of all meteorites that fall to Earth are chondrites, like Grimsby.
Studying this one in a lot more detail is very worthwhile because we want to be able to relate it to other ordinary chondrites.
Now that they know what type it is, the team needs to get a look inside to extract the evidence it may contain. And that's where this cutting-edge 3D X-ray scanner comes into play. The Grimsby meteorite could set a new standard in understanding how the majority of meteorites arrive on Earth.
The reason in this particular instance that we do a lot more measurements and try to get a better feel for what the meteorite really is composed is because we have this astronomical information. It puts it into this broader sort of solar system context. It's because we have this wealth of additional information on this event that it really warrants a full, complete workup.
The team is building a 3D image of the meteorite using a cutting-edge device called a micro-CT scan.
So this is a totally natural fragment of the meteorite. We haven't cut it, we haven't done anything with it yet. So we're very keenly interested to see what's on the inside of this one.
Like a CAT scan in medicine, this technology will allow them to look inside the meteorite without having to cut or destroy any part of it, preserving its structural integrity.
So a regular X-ray just takes all the information in an object and squashes it into one view. But in this case, when we finish the reconstruction, we'll be able to go through and select any plane or location within it and see what's there and measure the structures.
When the scan is complete, McCausland is able to navigate through the interior of the meteorite in 3 dimensions.
So here with Grimsby, I'm impressed by the fact that we're seeing these larger chondrules of a few millimeters in size, intermixed in a matrix of a lot of smaller chondrules and other material. That's something that I haven't seen very much of in other meteorites.
The chondrules are clumps of crystallized minerals. They are among the oldest material in our solar system, formed 4.5 billion years ago.
Ordinary chondrites generally are basically a grab bag of material from the early solar nebula. I mean, think of people up in the space station, you have a bit of water. If you let water out of a container, it goes bloop and forms this little bubble that floats there. That's what these chondrules are doing when they're melted rock by some heating event in the early solar nebula. All these chondrules are little solidified droplets of material,
which over time formed the planets and asteroids of our solar system. The team identifies a particular chondrule that they want to examine more closely and cuts a sample from the rock using a diamond-studded wire saw. The cut needs to be extraordinarily precise, and it takes more than 2 hours to complete. The university's scanning electron microscope team can now examine this sample.
So one of the unique things this instrument can do is not only give us chemical information on these crystals, but their structural information.
These images are at 1,000 times magnification. The chondrules in the Grimsby meteorite appear to be shattered.
These are like little nanoscale San Andreas faults, and this instrument can give us their structural and deformation history to put together the whole story.
From the solar nebula, you have the first solid objects forming, microplanets and so on like that. What happens whenever you start having enough solid objects forming is asteroids, small bodies, minor planets, they all will start running into each other.
These chondrules are a record of those collision events. Because the Grimsby meteorite is one of the best documented meteorite falls in history, it's providing hard evidence on both where meteorites come from and how they arrive on Earth.
For any one event like Grimsby, we're not going to say this meteorite comes from this asteroid, but by adding many of these events together, we get a probabilistic map that's built up that gives us a much better handle on where these objects are coming from.
By the team's calculations, the Grimsby meteorite probably originated in the part of the asteroid belt closest to Earth, about 250 million miles away.
We can start to make that bridge, going from a rock in hand and going back through the fireball event and get back to the asteroid belt. Given enough of these events like Grimsby, if we get a number more of them, maybe another dozen of these events, we'll be able to really start figuring out where these things come from in the asteroid belt.
And connecting meteorites back to the parent body that spawned them is the holy grail of asteroid science, a major leap in helping understand the origins of our solar system.
We're sort of painting a broad canvas, and each time we recover another ordinary chondrite with an orbit, we're putting one stroke on that canvas to add up to a more complete picture. Once we have many dozens of these kinds of meteorites in hand with orbits, we'll have a much better understanding of how asteroids and meteorites are related and how the delivery mechanisms work in more detail.
In the weeks following the Garchinsky find, McCausland and Brown recovered 12 more pieces of the Grimsby meteorite. And the University of Western Ontario's all-sky camera network continues to peer into the heavens, ready for the next fireball, one that will take them another step closer to filling in the picture of just how our world began.